Welcome to this problem walkthrough. Today, we'll explore problem number 768, max chunks to make sorted 2. This problem challenges your understanding of arrays and partitioning strategies, making it an interesting exercise in problem solving. Let's dive in and break it down step by step. In this problem, you are given an integer array ARR of length n, and the goal is to split it into some number of non-empty contiguous subarrays, which we call chunks. After sorting each chunk individually and concatenating them, the result should be the same as the sorted version of the original array. The objective is to determine the maximum number of such chunks that you can create. The input is the array ARR, where the length n can range from 1 to 2000, and each element can have a value between -10 to the power of 6 and 10 to the power of 6. The output is a single integer, representing the maximum number of chunks that meet the condition. This problem challenges us to think about how to divide the array strategically while ensuring that sorting and merging the chunks reconstructs the sorted array. Let's explore some examples to clarify this further. Consider the first example, where the input array is 5, 4, 3, 2, 1. The output in this case is 1. Here's why: the entire array is sorted in reverse order, so no matter how we attempt to split it, sorting individual chunks cannot produce the sorted array 1, 2, 3, 4, 5, unless the entire array is treated as a single chunk. Therefore, the maximum number of chunks we can create in this case is just 1. This example demonstrates that when the array is in strict descending order, the number of chunks is limited to 1. Now, let's look at a more interesting example with the input array 2, 1, 3, 4, 4. The output here is 4. To achieve this, we can split the array into the following chunks: 2, 1, 3, 4, and 4. Sorting each chunk individually gives 1, 2, 3, 4, and 4. When we concatenate these sorted chunks, the result is 1, 2, 3, 4, 4, which matches the sorted version of the original array. This shows that it's possible to divide the array into 4 chunks while ensuring the condition is satisfied. Notice how the splitting is influenced by the boundaries where the sorted condition is preserved. Let's consider another example with the input array 1, 1, 0, 0, 1. Here, the output is 1. The explanation is that the array cannot be split into multiple chunks such that, after sorting and concatenating the chunks, we get the sorted array 0, 0, 1, 1, 1. The only way to achieve this is by treating the entire array as a single chunk and sorting it as a whole. This example demonstrates how overlapping or unordered values can constrain the number of chunks we can create. Finally, let's discuss some edge cases. If the array contains only one element, the maximum number of chunks is always 1 because the array is inherently sorted. For an array where all elements are identical, each element can be treated as its own chunk, allowing the number of chunks to equal the array length. If the array is already sorted, each element can again be treated as its own chunk, maximizing the number of chunks to the length of the array. On the other hand, if the array is sorted in descending order, the entire array must be treated as one chunk, as no smaller divisions would satisfy the condition. These edge cases help illustrate how the structure of the array affects the solution. To solve this problem, one intuitive but highly inefficient approach is to try all possible ways to split the array into chunks. This brute force approach involves generating every possible partition of the array and checking whether sorting each chunk individually results in the entire array being sorted. While this may seem theoretically correct, the issue arises from the sheer number of possible partitions, which grows exponentially with the size of the array. For example, for an array of length n, there are 2 to the power of n subsets to consider, and sorting each chunk further compounds the computational complexity. This makes the brute force approach impractical for all but the smallest inputs, as it quickly becomes infeasible for larger arrays. The exponential growth in complexity is the key drawback here, ruling out this method as a viable solution for real-world scenarios. A much more efficient solution is based on a greedy approach that leverages the problem's inherent properties. The main insight here is that we can determine valid chunk boundaries by comparing the maximum value seen so far during a left-to-right traversal with the minimum value encountered during a right-to-left traversal. Specifically, if the maximum value of the left segment up to index I is less than or equal to the minimum value of the right segment starting from index I plus 1, we can safely define a chunk ending at I. To implement this, we construct two helper arrays, one, max_left, to store the maximum values from the start of the array up to each index, and another, min_right, to store the minimum values from each index to the end of the array. By traversing the array and comparing these two arrays, we can efficiently count the valid chunk boundaries. This approach runs in linear time, O(n), as constructing both arrays and performing the final comparison each require a single traversal. The beauty of this method lies in its simplicity and its reliance on the sorted property being preserved by ensuring the left segment's maximum does not exceed the right segment's minimum. The chosen strategy for this problem is the greedy approach using maximum and minimum arrays. This strategy is built on key observations about the nature of valid chunks. Specifically, a chunk is valid if the elements up to its endpoint can be sorted independently without disrupting the overall order of the array. By leveraging the max_left and min_right arrays, we can systematically identify these chunks in a single linear pass. The breakthrough in this approach was realizing that we don't need to sort within chunks at all. Instead, the comparison of the maximum value of the left segment with the minimum value of the right segment is sufficient to ensure the chunks can be sorted independently. This insight transforms what could have been a computationally expensive task into an efficient linear time solution. The simplicity of this algorithm, combined with its efficiency, makes it well suited for handling large arrays, as well as edge cases like arrays with duplicates or those that are already sorted. When comparing the brute force and greedy approaches, the differences in efficiency and practicality are stark. The brute force method is computationally prohibitive, with an exponential time complexity that makes it unsuitable for all but the smallest inputs. In contrast, the greedy approach operates in linear time, making it far more efficient and scalable. While there are potentially other methods, such as using segment trees, these alternatives often introduce unnecessary complexity without providing significant benefits over the greedy solution. The greedy approach strikes the right balance between simplicity, efficiency, and correctness, directly addressing the problem's requirements while remaining easy to implement. This makes it the optimal choice for solving the problem, as it handles both typical cases and edge scenarios effectively. To solve this problem, we need to split the array into the maximum number of chunks. The key insight here is that a chunk is valid if sorting it and concatenating all chunks results in the entire array being sorted. This means that for any split point, all elements in the left chunk must be less than or equal to all elements in the right chunk. To achieve this, we will use two auxiliary arrays, left_max and right_min. The left_max array will store the maximum value from the start of the array up to each index, while right_min will store the minimum value from each index to the end of the array. These arrays allow us to efficiently determine the boundaries for each chunk. Let's start by populating the left_max array. Initialize it with the first element of the input array, and as we iterate through the array, each index in left_max will hold the maximum value seen so far. This creates a running record of the maximums from the left side of the array. Once the left_max array is populated, it will contain the largest value from the start of the array up to each index. Similarly, we initialize the right_min array with the last element of the input array. Then, as we iterate backwards through the array, each index in right_min is updated to hold the smallest value seen from that index to the end. This ensures that right_min contains a running record of the minimums from the right side of the array. With these two arrays, we can now traverse the input array and compare values at each potential split point. Specifically, if the maximum value in the left chunk, given by left_max, I, is less than or equal to the minimum value in the right chunk, given by right_min, I+1, then we know the split is valid. For every valid split, we increment a counter to track the number of chunks we can form. Once we have counted all the valid splits, we add 1 to the count to account for the final chunk, which extends from the last valid split to the end of the array. This approach guarantees that the array, when split into these chunks, can be individually sorted and concatenated to produce the fully sorted array. There are a few key takeaways here. First, the condition for a valid split ensures that sorting each chunk independently will not disrupt the overall order of the array. Second, using the left_max and right_min arrays allows us to solve the problem in linear time, as we only need a few passes through the array. Finally, the algorithm handles edge cases like arrays that are already sorted, arrays in reverse order, and arrays with duplicate values seamlessly. For example, if the array is already sorted, each element can form its own chunk, and if the array is in reverse order, only one chunk is possible. Analyzing the complexity of this approach, the time complexity is O(n). This is because populating the left_max and right_min arrays each requires a single pass through the input array, and counting the valid chunks requires another pass. Thus, the overall time complexity remains linear. In terms of space complexity, the algorithm uses two auxiliary arrays, left_max and right_min, each of size n. Therefore, the space complexity is O(n). This efficiency makes the algorithm well-suited for even large input arrays, as it minimizes both time and space usage while maintaining clarity and correctness in handling the problem requirements. This implementation efficiently solves the LeetCode problem number 768, max chunks to make sorted 2. The goal is to split the array into the maximum number of chunks such that sorting each chunk and concatenating the results produces a fully sorted array. The solution uses two arrays, max_left and min_right, to determine the boundaries of each chunk. 1. Step 1. Compute max_left. This array keeps track of the largest value encountered from the start of the array up to each index. This allows us to determine the maximum value for the left side of a potential chunk. 2. Step 2. Compute min_right. This array keeps track of the smallest value encountered from the end of the array up to each index. This allows us to determine the minimum value for the right side of a potential chunk. 3. Step 3. Iterate through the array and compare max_left, I, and min_right, I plus 1. If the maximum value on the left side is less than or equal to the minimum value on the right side, it means a valid chunk boundary exists. Increment the chunk count. For final step, add 1 to the chunk count to account for the last chunk, which is always valid. The algorithm runs in O(n) time since it involves a single pass to compute max_left, another for min_right, and a final pass to count chunks. This makes the solution efficient and appropriate for large inputs. Edge cases, such as already sorted arrays or arrays with duplicate elements, are handled naturally by the logic. Here, we begin by importing the necessary libraries and defining the solution class. The core function, maxChunksToSorted, takes an integer array as input and aims to calculate the maximum number of chunks we can divide the array into, such that sorting each chunk individually will result in the entire array being sorted. To achieve this, we start by initializing two arrays, maxLeft and minRight. The maxLeft array will store the maximum values encountered as we traverse the array from the left, while minRight will store the minimum values as we traverse from the right. First, we populate maxLeft. The initial value is simply the first element of the array, and for each subsequent index, we store the greater of the current array value or the maximum value up to the previous index. Similarly, we calculate minRight by starting with the last element of the array and moving backward, storing the smaller of the current array value or the minimum up to the next index. These two arrays help us determine boundaries where the array can be split into valid chunks. With maxLeft and minRight computed, we can now determine the number of valid chunks. By iterating through the array, we compare the maximum value in maxLeft up to the current index with the minimum value in minRight starting from the next index. If the maximum value on the left is less than or equal to the minimum value on the right, it indicates that the current index is a valid boundary for a chunk. We increment the chunks counter each time such a boundary is found. Finally, we return chunks plus 1 because the last segment of the array will always form a valid chunk. This implementation efficiently calculates the result in O(n) time, making it suitable for large inputs. To solve this problem, we aim to split an array into the maximum number of chunks where sorting each chunk individually and then concatenating them results in a completely sorted array. Unlike the simpler version of this problem, here we must also handle duplicate values in the input. Let's begin by initializing the necessary structures. First, we determine the size of the input array, which in this example is 9. Then, we create two auxiliary arrays, max_left and min_right. Both are initialized to 0 and have the same size as the input array. The purpose of these arrays is to help track the maximum value from the left side and the minimum value from the right side for any given position in the array. Next, we construct the max_left array step by step. We start by setting the first value of max_left to the first value of the input array, which is 2. Then, for each subsequent index, we compute the maximum value between the current value in max_left and the corresponding value in the input array. For example, at index 1, the maximum of 2 and 1 is 2. Continuing this process, we eventually build the complete max_left array, which becomes 2, 2, 3, 4, 4, 6, 6, 8, 9. This array now represents the maximum value encountered from the start of the input up to each position. Now, we construct the min_right array, which works in a similar way but in reverse. Starting from the last element of the input array, we set the last value of min_right to the last value of the array, which is 9. Then, for each preceding index, we compute the minimum value between the current value in min_right and the corresponding value in the input array. For instance, at index 7, the minimum of 9 and 8 is 8. Repeating this process, we eventually construct the full min_right array as 1, 1, 3, 4, 4, 5, 5, 8, 9. This array now represents the minimum value encountered from each position in the input to the end. With both auxiliary arrays built, we can now count the number of chunks. To do this, we compare the values in max_left and min_right for adjacent indices. Specifically, for any index I, if max_left I is less than or equal to min_right I plus 1, it means we can split the array at that point. Starting at index 0, we find that the condition is false. However, at index 1, the condition is true, so we increment the chunk count to 1. We continue this process until the end, finding a total of 5 valid splits. Adding 1 for the final chunk gives us an output of 6 chunks for this example. Let's look at another example where the input array is 1, 0, 2, 3, 4. We begin by initializing the structures. The size of the array is 5, so both max_left and min_right are initialized as arrays of zeros with length 5. First, we build the max_left array. Starting with the first value, which is 1, we then calculate the maximum at each index by comparing the current value in max_left with the corresponding value in the input array. This results in max_left equals 1, 1, 2, 3, 4. Next, we construct the min_right array. Starting from the last value of the input, which is 4, we compute the minimum at each index by comparing the current value in min_right with the corresponding value in the input. This gives us min_right equals 0, 0, 2, 3, 4. Once both arrays are ready, we count the chunks. By comparing max_left I with min_right I plus 1 for each index, we find valid splits at certain positions. For instance, at index 1, the condition holds true, so the chunk count is increment. Continuing this, we find a total of 4 valid splits, and adding 1 for the final chunk gives us an output of 5 chunks. Finally, consider the input array 4, 2, 2, 1, 1. In this case, the values overlap heavily, making it impossible to split the array into multiple chunks while maintaining the sorted order after concatenation. Since no valid splits can be made, the entire array must be treated as a single chunk. As a result, the output for this example is simply 1. Here, we analyze the time complexity of the solution, breaking it into 3 main steps. First, we build the max_left array. This involves a single pass over the input array, where we calculate the maximum value at each index by comparing the current element with the maximum so far. Each comparison takes constant time, and since we process all n elements, this step runs in O(n). Next, we construct the min_right array by iterating through the array in reverse. Similarly, for each index, we compute the minimum by comparing the current element with the minimum of the next index. Again, this is a linear pass with constant work per element, contributing O(n). Finally, we count the chunks by iterating through the array and comparing values between max_left and min_right. This involves one additional linear pass with constant work per comparison, adding another O(n). Each of these steps contributes linearly to the total time, making the overall complexity of the solution O(n). Adding up the time complexities of all the steps, we get O(n) plus O(n) plus O(n), which simplifies to O(n). Now, turning to space complexity, the input array itself does not require any additional space since it is given to us, contributing O(1). However, we use two auxiliary arrays, max_left and min_right, each of size n. These arrays store the maximum values from the left and the minimum values from the right, respectively, and their space usage adds up to O(n) plus O(n), which simplifies to O(n). Additionally, we use a few scalar variables like the array size, counters, and loop indices, all of which require constant space, contributing O(1). Therefore, the total space complexity is dominated by the two auxiliary arrays, resulting in O(n). The overall space complexity remains O(n), primarily due to the max_left and min_right arrays. Comparing this optimized solution to a brute force approach highlights its efficiency. A naive method would involve attempting all possible partitions of the array. For each partition, we would need to verify that the maximum of the left subarray is less than or equal to the minimum of the right subarray. This verification process would require nested iterations, leading to a time complexity of O(n squared). By contrast, the optimized solution avoids redundant calculations by pre-computing the max_left and min_right arrays in linear time. This allows us to count chunks with just a single pass, reducing the time complexity to O(n). This improvement makes the solution much more scalable for large input sizes. To understand this solution's performance further, we examine the best, average, and worst-case scenarios. In the best case, when the array is already sorted or reverse sorted, the operations to compute max_left and min_right still require linear time, resulting in O(n). In the average case, the algorithm remains O(n), as its complexity does not depend on the input's distribution. Even in the worst case, for highly unsorted arrays, the algorithm performs the same linear operations, ensuring a time complexity of O(n). Mathematically, we can prove this by noting that each of the three main steps, constructing max_left, constructing min_right, and counting chunks, requires a single pass over the array, each contributing O(n). Summing these together confirms the total time complexity is O(n). Similarly, the space complexity stems from the two auxiliary arrays, each of size n, leading to O(n). This linear behavior in both time and space makes the solution optimal and robust for a variety of input scenarios. When solving problems like this, it's important to avoid common pitfalls that can trip you up. One frequent mistake is assuming that a single, fixed way of partitioning the array will always work. Problems involving splitting an array often require dynamic decisions based on the values within the array, so a rigid or predefined approach typically fails to handle edge cases. Speaking of edge cases, overlooking scenarios like arrays that are already sorted or those with only one element can expose weaknesses in your logic. Be sure to explicitly test for these cases. Another common issue is incorrectly verifying the sorted result. For example, simply checking if an array matches its sorted version without considering intermediate constraints can lead to false positives, as the intermediate state might not meet the problem's requirements. Lastly, be mindful of inefficiency for larger inputs. Solutions with high time complexity, such as O(n cubed, might work for small test cases but will fail when dealing with inputs that are significantly larger, such as n greater than 10,000. Always aim for scalable solutions. Another important consideration is to fully understand the constraints provided in the problem. For instance, constraints like non-negative integers, uniqueness, or specific value ranges can often simplify your approach and guide you toward an optimized solution. Ignoring these constraints might lead to unnecessarily complex logic. In interview settings, it's also vital to clarify the requirements up front. For example, does the interviewer expect non-overlapping chunks, or are there constraints on the chunk size? Such clarifications can dramatically simplify your problem-solving approach. Additionally, looking for patterns is key. Many partitioning problems, including this one, have underlying mathematical or greedy patterns, such as tracking maximum values or cumulative sums. Recognizing these patterns early can unlock the solution. Finally, always be prepared to discuss the time and space complexity of your approach and explore potential trade-offs. For example, while a greedy solution might be faster, it could require additional space. Walking through small test cases manually is also highly recommended during interviews. This allows you to explain your thought process clearly and verify your solution step by step. When exploring related problems, it's helpful to see how this problem connects to others with similar themes. For example, LeetCode problem 769, the first version of this problem, involves simpler constraints and is a good starting point. Problems like merge intervals, problem 56, and trapping rainwater, problem 42, also involve partitioning or combining sections based on specific conditions. Another interesting connection is problem 295, where you're tasked with maintaining a running median, which also relies on dynamic data handling. Beyond related problems, there are alternative approaches to consider for this problem. A greedy approach, for instance, is often faster with a time complexity of O(n), but it requires careful justification to ensure that making a local optimal choice leads to the correct global solution. Using prefix and suffix arrays is another option. This can simplify the logic by pre-computing necessary information, but it does come at the cost of additional space, typically O(n). Divide and conquer is yet another method, where the problem is broken into smaller subproblems. However, this can introduce recursion overhead and might complicate the merging of results. Choosing the right approach depends on the specific scenario and the constraints provided in the problem. To wrap things up, there are a few key insights to keep in mind when tackling this type of problem. The most important step is identifying the key property that validates the split. For example, a common property is ensuring that the maximum value in one chunk is less than or equal to the minimum value in the next chunk. This property is often central to the solution. Clarity in implementation is another critical factor. Breaking your solution into modular helper functions not only improves readability but also makes it easier to debug and explain your logic. Testing edge cases is essential as well. Be sure to account for scenarios like very small arrays, arrays that are already sorted, and arrays with duplicate values, if they're allowed in the problem constraints. By focusing on these principles, you can develop robust, efficient solutions and demonstrate a strong understanding of the problem both in practice and during interviews. Great job working through this problem. Today, we learned how to partition an array effectively using prefix maximums and suffix minimums. This approach emphasizes the importance of pre-computing data for efficiency. Practice similar problems to solidify your skills, and don't forget to like and subscribe for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!